In this video, I'd like to just go through a couple limits that often arise when we're working on improper integrals. In particular, what I hope to do is just remind ourselves what plots of these functions look like, so we can more easily draw what their limits are as x goes to infinity. And then the last example, we're going to see that we're going to reuse our friend L'Hopital's rule to actually help us compute a limit. So let's get going with this. So the first function we have is the limit as x squared, limit of x squared as x goes to infinity. So you might remember the x squared sort of does an upwards trend in a parabolic shape. And as x goes to infinity, remember what we're wondering about is as x goes, increases and increases and increases, what is happening to our function? In this case, well, as x is increasing, again, x moving to the right, what's happening to our function is it's always perpetually moving upwards. So this limit is a positive infinity. Now the next function, or problem 2, let's look at is the limit of the function 1 over x as x goes to infinity. So in this case, remember, when we have a giant number in the denominator, the overall fraction is going to get smaller and smaller. So in this case, as x increases, what we're going to see is that the denominator increases a lot. So 1 over a very large number that's just getting larger and larger, that's going to get smaller and smaller. In particular, what this function looks like is the following. So we have more or less a horizontal asymptote as x goes to infinity at 0. So this limit in particular is equal to 0. Now, the other thing I just want to mention here is if we're interested in a somewhat similar looking function, say the limit as x goes to infinity of 1 over x squared, well, what does 1 over x squared look like in comparison to 1 over x? Well, the denominator of 1 over x squared, that denominator is going to be larger than just the denominator in 1 over x. So in this case, the overall fraction in 1 over x squared is going to be a lot smaller than just the fraction 1 over x. So if we're to plot what the function 1 over x squared looks like, it looks something like the following, where there's also a horizontal asymptote at 0 for 1 over x squared. Well, 1 over x squared is going to be smaller than 1 over x. Either way, though, both of these limits, they equal 0. All right, let's move on to the next one. The limit as x goes to infinity of e to the x. Now, e to the x is an exponential function that's always going to increase. In particular, when x equals 0, e to the x takes on a value of 1, and then we're going to see exponential growth from it. So as x goes to infinity, e to the x is also going to infinity as well. Now let's contrast that to the limit as x goes to infinity of e to the minus x. And remember, we could also write e to the minus x as a 1 over e to the x through some algebra. Since the power is negative, we can put that term back into the denominator. So as x goes to infinity, we're seeing in this case, if this exponential is now in this denominator, this e to the positive x in that denominator is getting very, very large as x going to infinity. So we're expecting this overall fraction to be small. And in fact, well, e to the minus x, what this function looks like is at x equals 0, e to the 0 is just 1, and then it exponentially decays where we see we have an horizontal asymptote at 0. So as x goes to infinity in this case, this limit of e to the minus x, or the limit of 1 over e to the x, that's equal to 0. So moving on, let's now look at the limit of the ln of x, the natural log of x, as x goes to infinity. So there's a couple things for us to picture of this natural log function. we know when x equals 1, the natural log takes on a value of 0, and then it grows very, very slowly after that. So this value of natural log, it does grow slowly, but more in particular, it grows slowly towards positive infinity. So just saying, the natural log grows slowly, but it does grow towards positive infinity over as x increases. Now for values between 0 and 1, the natural log actually takes a dive down towards minus infinity. So maybe it's worth putting here as well, that not only does the natural log of x go to infinity as x goes to infinity, but the limit as x goes to 0 of the natural log of x is equal to minus infinity. So the natural log of x as x goes to infinity grows to infinity, but the natural log of x as x goes towards 0, that goes towards minus infinity. All right, so I think those are a bunch of popular functions that we often see arising in these improper integral problems. The last thing I want us to do is really practice a problem where we're going to get to use L'Hopital's rule. So as a spoiler, we're going to get to use L'Hopital's rule on this problem. Now, what I want us to look at is, in this limit, we have the product of two functions. We have the product of this x and the product of e to the minus x. Why this is important is we could think about each of these functions individually, see what they do as x goes to infinity, and reassess the limit that way. So remember, if we're just plotting something like x, well, that's just a line. So as x goes to infinity, that x alone wants to go towards infinity. However, if we were to plot that decaying exponential, or e to the minus x, what that function does is that function goes towards 0 asymptotically, or it approaches 0 as x goes to infinity. So remember, neither of these things is exactly infinity, exactly 0. Limits are all about what's approaching what. In this case, it looks like this x is growing towards positive infinity. This decaying exponential is going towards 0. So we have this situation that looks like a 0 times infinity. And well, at this stage, we can't say this is 0. We also can't say it's infinity. So we get to do a little more work, basically to see which of these functions wins. And this extra work we get to do, this is where we can do a little bit of algebraic massaging to turn this into a L'Hopital's problem. So remember, in order to use L'Hopital's, we need something that looks like a infinity over infinity situation, or we need a 0 over 0 situation, so-called indeterminate forms. In this problem, we don't exactly have one of those indeterminate forms because we have something that looks like an infinity times a 0. And well, in these situations of infinity times 0 looking things, we can use algebra, like I mentioned a moment ago, to turn this into one of these indeterminate forms, either an infinity over infinity situation or 0 over 0 situation. And then we can apply L'Hopital's rule. So we do a little bit of algebra first, and then apply L'Hopital's rule. So let me just rewrite this limit. So we have the limit as x goes to infinity of x e to the minus x. That's just our original problem. And now we have to figure out, well, how can we turn this into one of these indeterminate forms? Basically, we need to try and make this into a fraction using algebra. And well, this decaying exponential, we know we can rewrite this as a 1 over e to the x. So we could rewrite this product as an x over e to the x. And now when we see what happens in this case, as x goes to infinity, Well, that numerator is looking like infinity, and as x goes to infinity, this denominator by itself looks like it's going towards infinity. So we're sitting in an indeterminate form now. And now, because we're sitting in an indeterminate form, we can apply L'Hopital's rule, because when we kind of just glance at this limit, it looks like infinity over infinity, indeterminate, apply L'Hopital's rule. So the way L'Hopital's rule works is we take the derivative of the numerator and denominator separately, because what L'Hopital's rule really wants to know is how fast are these functions growing or how fast are these functions shrinking? So it's really about how fast or the change of these functions. So in the numerator, taking the derivative of x, that just gives us a 1. In the denominator, taking a derivative of e to the x, that gives us an e to the x. And now when we reassess this limit, after doing one thing of L'Hopital's rule, we ask ourselves what's happening in the numerator, what's happening in the denominator. So in the numerator, well, as x goes to infinity, that's just looking like a 1. So I'm just going to write kind of what I'm thinking. I have a 1 in the numerator. So I'm just going to say this is what I'm thinking. In that denominator, as x is going to infinity, well, e to the minus x, that thing's going towards infinity. So what this looks like is we have a constant number, just a 1, sitting over something that's growing and growing and growing, something that's over infinity. So what this overall limit looks like is 0. So in this last example, we're able to apply L'Hopital's rule to a problem that right from the bat, instead of looking like, well, a 0 over 0 or infinity over infinity situation, it looked like a 0 times infinity. So we used a little bit of algebra to massage this into an indeterminate form so we could then apply L'Hopital's rule.